Today's class we are going to talk about dynamic programming, which is another design principle technique to devise efficient solutions. Dynamic programming is a design principle that is usually used for optimization problems. We have discussed few other design principles. One was divide and conquer, and the other one was greedy algorithms. So greedy algorithms and dynamic programming both are normally used to solve optimization problems. So let's see what is different in dynamic programming for greedy algorithms and how we can apply dynamic programming to solve optimization problems. Along with that, what are the key properties that should. Okay, so greedy algorithm, as I said earlier, and the dynamic programming algorithms are both two different methods to solve optimization problems. Greedy algorithms are generally more efficient than dynamic programming solutions because of the nature, the way we solve the optimization problems using greedy algorithms. In greedy algorithms, we generally devise a greedy heuristic and we solve our problems as a sequence of decisions or choices. Greedy algorithms are efficient because based on our greedy heuristic, we make a choice or make a decision, and over the course of algorithm, we do not change any decision once we decide upon it, right? So that's why the greedy algorithms are generally much more efficient. And the hard part about greedy algorithms is that since we are not exploring all the possibilities, so we are not sure that we will always get the optimal solution, right? So in our previous classes we have also seen that in many cases we have to provide a proof of correctness. Nevertheless, there are many problems that cannot be solved using greedy algorithms, or to make it more precise, there are many problems for which we do not know any greedy heuristics that can be applied to those problems that guarantees the optimal solution whenever that heuristic is applied, right? So what are the other options? So normally, as we have discussed earlier, in optimization problems, enumerating all the possible choices is not feasible or tractable, because all feasible choices are or feasible options are generally exponential in number, and for a fairly large size problem we cannot apply that solution, right? So the next idea is, let's apply another design principle which is called dynamic programming. Dynamic programming is generally lesser efficient than greedy solutions, but we'll see that for a good set of optimization problems, we can solve them using dynamic programming that are not as efficient as greedy algorithms, but they are much more better than the brute force approach. Generally, the idea behind dynamic programming is that we try to prune the search space that we have to explore, right? And that pruning actually helps us in devising efficient solutions. So the idea is that we generally explore the space of all the possibilities, all solutions, right? So it is similar to the brute force approach, but because of certain properties, we are able to devise polynomial time solutions for various problems. And the two basic things that we need in dynamic programming is that all those problems that we solve using dynamic programming should have optimal substructure within them. We'll see shortly what is the optimal substructure. Generally, we devise a recursive solution to the problem in which we want to solve the smaller subproblems, and then using the solution of those smaller subproblems we solve the original problem, right? So you might ask that then what is different in dynamic programming than divide and conquer approaches. So the basic difference in dynamic programming and divide and conquer design principle is that in case of divide and conquer, we are generally get two or sometimes more than two independent subproblems. Every subproblems is a new one. But in case of dynamic programming, many times we saw the phenomena which is called subproblem overlapping. So we can use that idea to make efficient solutions. So the key idea behind dynamic programming is that we use the trade-off of time versus memory or space. We use more space to reduce our time requirement, right? So we devise a recursive solution for the original problem. That means we need a mechanism in which we can describe the original problem into a bunch of subproblems. Subproblems mean the same problem with the smaller size, and by computing the optimal solutions of those subproblems, we can compute the optimal solution of the larger problem, and this property is called optimal substructure. I'll explain you in detail shortly. Generally, we make an array or a table in which we store the solutions of the subproblems, because subproblem overlapping occurs, and instead of recomputing again and again the same problem, we usually store them once we compute them, and next time whenever we need that solution, we simply need a constant time, we require a constant time lookup, and we simply get the solution. So time is saved by both these properties. Since there are subproblem overlapping, so instead of recomputing again and again, we save time by employing more space. And because of this optimal substructure property, we know which solutions to explore and which to not. So the first and foremost question is, for what kind of problems we can use dynamic programming? So dynamic programming are generally used for problems that have the optimal substructure property in it. That means that we will require the optimal solutions of the subproblems to solve the original problem. That means we only need to solve the subproblems for their optimal answers, and we do not need to check the suboptimals ones, right? Generally, what we do is we devise a recurrence relation that tells how to solve a larger optimization problem using the optimal solutions of its subproblems. And most of the cases, it turned out that these subproblems are overlapping subproblems, because the same subproblem may occur many times in the recursion tree. So we can, instead of recomputing all those things again and again, we can reduce the time requirement by storing the solutions or the answers of those subproblems in the memory. We only compute them once, and we then reuse them whenever they are required.